Hi, welcome to this last part of this Ahmed body tutorial, and in this last one we're just going to do a little bit some post-processing. We previously did something with paraview. I'm going to show you some new stuff if you don't know that, and also some basic sampling just to finish this tutorial. Then if we have time, or you are going to release new tutorials, more advanced stuff and multi-phase flows and more mesh generation and solid modeling. So I already ran this tutorial, but I was just want to show you a few stuff. Like for instance, previously we were looking at the solution, but as well as you didn't follow that one, remember that there are a few utilities. I will use this utility to take a look at the solution. So I previously saved my solution, the log file. Remember, always save those log files, they are really important. So here I have the history of the convergence of my solution, but also I can plot, and I have a new plot here. So in the folder new plot, you will find this script that will plot your force coefficients on the fly. Okay, here see, not running doesn't matter, but as you are running a simulation, you will see the evolution of your solution. So basically what is important here, we're running simple flow, and I let it run up to 1000 iterations. Maybe that was unnecessary. Maybe I could stop in 500, so probably less. And one of the question people always say is newcomers and CFD, I running steady simulations, why my solo simulation is converting. Remember, steady doesn't exist in reality. It is kind of a trick that we have just to get fast outcomes. So here, this simple, that the fact that it's not converted is just an indication that your solution is in reality on a steady. And we know this problem that we have those vortices on the back of the model. We have some vortex shedding and some detached flow. So this is in reality is highly unsteady, but this steady solution solver will never converge. Okay. And here kind of you can see in this monitor that we are reaching a periodic solution, that you see how my coefficient is oscillating in time, is repeating as well, lift and drag. So here we have lift coefficient, here we have drag coefficient. So it's not only about looking at the residuals. For me, it's more important measuring a quantity of interest and monitoring that quantity. Something I was telling that we would like to do some validation. So this case has extensive validation. We're running for an angle of 35, if I would recall. And you can go Google this, look on the internet, and you will find many data. But probably we're not 100% on agreement with the data, but we're there. We're in the ballpark now. We're in the area. We have the CD. Okay, we can also compare a little bit with CD if it's reported. But besides that, also we have the information, velocity information that we sample. In this case, we have the script there. And just to show you, in your folder, is you download the case in the link that you will see in the screen. You will have the folder experimental, and here we have all the experimental data. Okay, so as you open one file, you will see what was measured. Okay, the x, its y and z coordinate velocity. So basically we can compare the height and the horizontal velocity for each of these positions in x, and here you have the Excel worksheet that you can open with all the experimental data. I won't go into details with that. You have there the script. You can use new plot, for instance. I already prepared a script there. So you use duplet script 1, and this is all the data that we sample. Okay, so these are your velocity profiles. Okay, so horizontal velocity, vertical height, so you see your velocity. Then for instance we can have something like this where we plot experimental results again, the CFD simulation. I still need to work a little bit. This is great. Probably you can also finish this one, but what we would like to do is just compare this. So you will have your CFD simulation, this continuous light, and the experimental simulation. So remember, it's not about all those pretty colors. Also, you need to give some quantitative validation. What else do I need to tell you? I think pretty much, yes, we can close this one. That was about monitoring, plotting some stuff in your solution. And at this point I can show you just the last part of the post-processing with paraview. So we'll launch paraview, in this case paraphone, and I already prepared a small visualization here. Just I'm going to show you a few new filters that maybe you don't know. If you don't know, okay, it's not a problem. And remember, you have the option to say the state, what you have done in your simulation. So here I already save an state with many filters already applied, but you will find that one in the folder. I put it already there. In your case, paraview, and there you have that state. So we go here, load state. I have it here in this case, paraview. Okay. So I'm loading my solution. You see that in my Faceline browser I have many things going on here. I will explain to you what is everything. And always remember that we have this readme first file, but we have the steps that you need to follow. So basically here you will have how to generate the simulation, do some transformation. Here we're translating our mesh just to be to have the same audience and the experimental results. Run the simulation, and here we have the part of the sampling. So this is a way we're using OpenFOAM 4. So in OpenFOAM 4 they changed the way to do the post-processing. So this is the way how you compute your Y plus, Wolřej stresses, Q criterion, vorticity, and this is how we do sampling now. So this one will read a new dictionary called sample that it will find a system. So here, let me go, and this is our sampling. So here I just sampling many lines according to my experiments, the reference I found. So basically take this line from this position to the other and do the sampling of the quantity of interest, in this case velocity. So you will get many lines with all the components of velocity, and all that information you will have it saved in as usual post-processing will be called sample, and then you see the name you gave it in the dictionary, and as you open that file you will have here the component coordinates and then the velocity components. So let me show here now paraphone. So this is what we have, and I will show you a few things. A lot of people has asked me, okay, I want to plot a surface streamline, so I will show you how to do it. You see you have it there. So there are two approaches in paraview to do that, which I think I will show you both of them. So basically this is what we have, and I will show you this workflow quite fast what we have done. So the first thing that when you load, you will get one case, okay? So basically you get your original case, but something important that as you see here that we're applying filters over filters, we have the ability also to plot, for instance, only the body, and then I can do a slice. Okay, so this one is you have one case loaded, it's not possible. Okay, it's you apply a plane, then you won't see your geometry. So one solution is to load two cases, which is not very efficient if they are large, because you are loading twice a case more memory. So what you can do in OpenFOAM to avoid that of loading several cases, that you can apply a filter called extract block. So for instance, you load your case, okay, and then you select everything. Okay, you have all your parts, you select all your volume fields, and to use this extract block, you just come here in filters, alphabetical, and you have it here. So basically this what it's doing, extracting some selections of your mesh part. So look at that. In block 1, I only want to see internal mesh, and then in this internal mesh I can apply all those volume filters. Then I will have a second block where I will only see the patches Ahmed and ground. You see that I have it here. Okay, and then I will have a search block that only want the Ahmed body, that later I will apply another filter, but also I can do some forces computation. I can compute Wolৰীষ্টstresses. That can be done also in OpenFOAM. It's a little bit tedious, requires some picks and clicks and all the options, but it can be done here. It can be programmed in Python. We are going to do here. Probably later we are going to do another tutorial just dedicated to computing forces. That can be really handy. So I extracted this tree and I'm planning to do some operations in those blocks that I have. So for instance, in block 2, look at that, I have slices. So I have those 2 slices there. So in this one I can plot the velocity, and then I have a second slice where I can plot whatever I want. So not necessarily needs to be the same field. So look at it here, I'm plotting vorticity, and here vorticity gives you kind of indication of the rotation. So I will show you one other filter that is here, since I'm rotating kind of like this. But if I want to properly see how they are rotating, I can just plot vectors in this component. So there is a filter called surface vector. You can come here and you will have it somewhere here, surface vector, you see here. So you need to select your slice, filter, and then surface vector. When you select surface vector, remember select the vector, okay? You can have something different, for instance, you can have vorticity, whatever, and then select what is you want to do. So you have perpendicular, parallel. In this case, we want a parallel, and after you have that surface vector, that pretty much is plain like this, but now you will be able to plot the vectors here. So you select the glyph that I already did this operation. So you apply the glyph. You see here that we have the workflow. So I apply this glyph in surface vectors. See here that we can access those vectors, constrain it to that plane. So now we can see better the rotation. So you see that as we're expecting, we have those counter rotating vortices. And now, for instance, I have access also to Q criterion that I computed in OpenFOAM, but I will show you how to compute it also in paraview. So as I plot here, you see here that we have those vortices there. So they are not very well characterized. Remember, this is a quite coarse mesh, so it's part of your validation as well. Later, if you want, you can go find that meshes, do less or this. Maybe later we're going to do a new tutorial just to show you how to set up a less this and do some specific post-processing. But look at that, we have the vortices there, well characterized, and pass through those areas there. And for instance, remember that vortices are low pressure area, so you can plot pressure there and you will see that that is a low pressure area. So let me change the minimum, and you see that this is a low pressure. Okay, so basically our physics is kind of okay. So how do we question, how do we compute now this Q criterion and in OpenFOAM? So to do that, for instance, there are a few operations that I like to put in paraview, that I prefer to do in paraview. For instance, sometimes can be handier to do this kind of operation here because you get a smoother surfaces. But also, for instance, sampling, sometimes it's easier to do sampling, and sometimes you don't get the same problems that you have when doing the sampling in OpenFOAM. Sometimes you have problem running in parallel in boundaries as well. You can have strange stuff. So doing the sampling here is a way much better. So just get your script and then just repeat it. So but to compute here the Q criterion. So basically again we need access to the whole mesh. See that I'm still working in start extract block here. And the new filter is this one, gradient of unstructured dataset, that you will find it here. Okay, and if you come here, basically First, select your scalar array. So you select velocity. So what it's going to do is decompose that velocity into the three components, and then you can compute your Q criterion. So for instance, I think maybe you will have something like this. Okay, so you won't have access to Q criterion or vorticity. To access that information, you can enable advanced features here. So remember this button, always click here and you get more features. So see here that we have access to all those features. So we have here compute vorticity, Q criterion. So you just come here and just can get those quantities. And as soon as you have the Q criterion again, like we did with this previous solution, just plot surfaces contours, okay, and then choose a value for that quantity. Usually Q criterion is a positive quantity, okay. So you can choose something, you need to play around, but usually go and choose positive value about 100. If 100 shows you too much vorticity, probably try to increase it. So for instance, I put 10 here, it will capture too much, it will be a little bit difficult to visualize things. Okay, still okay, probably 1. You see it's capturing too much stuff and some noise, so you keep increasing that value. So I always start with 100 and then from there you just get a scaling, but remember it's always a positive quantity. So in this case we have 500, and as usual you can plot, for instance, velocity in that, and you can see velocities on those vortices. That's all. So now I would like to show you, for instance, we have this slice here, okay, and for instance I can plot in this slide, okay, I can get the same sampling that we got with sampling utility, we can get it here. So I already did that operation here, okay, so I can plot in this line, okay, and then you can here I already had show there, and you have access to that, to all that information. So for instance, I can choose on the X velocity and see that we have our X velocity and your coordinate, and we're plotted in this line. Okay, it's clear that here we don't have anything. So exactly what we do with sampling, we can do it here. Sometimes more comfortable here, sometimes better in paraview, so it's up to you. But remember, you can also export this data. So you get it here, select here, you see that you have this blue frame here. When you have this blue frame here, means that this is the view that is enabled. And go in File, Save Data, CFD, that is comma separated value, and then give it a name, for instance data out precision. I want to save the data in points, so you have different arrays with data, field association, some points will be okay. And then when you go here, you will have your file, and then you can plot it with NuPlot or Python, your default plotting tool. So see that we have the data here, and you see that where we have not a number is the part inside the body with that we don't have data, and then you have all the information, you access all the information here. Okay, so here you have the header, so you know what we're sampling, so we're getting everything here. So this is something additional as well, how to plot that data there. Let me hide this. So at this point, let me see what else I can do. So I have this body here, let me hide this size. So something that I want to show you is how to plot the surface lines, okay? So there you have two options to plot surface line. First, you need to compute the Wolშირ stresses in OpenFOAM or whatever software you're doing. You can also compute that quantity in paraview. It's very tedious. You need to create all those operations. I hope you remember how is it that tensor. You can do it here. Maybe in another tutorial we're going to do it, but here we start from the fact that we have that field. So the easiest option is to use a plugin called Flow League or Surface League. You see we have it here. So I will select this plot, better this one, okay, and I will select this option here. as soon as I select this option, I have access to, it's called line convolution, I think, if I will recall. And what I need to do is just select the Wolřejr field. You see I don't see nothing, because by definition in the wall is 0, but if you are doing an older computation, well, you can use U. So you select Wolřejr and see that you have that information here, okay? And you will have many options here how to control that. Remember, maybe you won't see all those actions because you need to access the advanced tab, but you have many options to control this line convolution, this surface leak filter, and see that you can see kind of all your streamlines. But some people say, okay, but I just want to see a few streamlines, or I want to release that in streamline for a particular part. So I will show you next how to do that. But to access by default, you cannot access this new representation. To access this one, you need to come to Tools. Here you will have this Manage Plugins, and you have it here, Surface Leak. Okay, you need to enable this one, and then you need to select the Auto Load option. You will need to close paraview and reopen it. Okay, but this is the way how you enable that one. In this case, I already have it. I will plot like this. So now I will show you the second option. Okay, the second option consists of, again, you need the Wolřejr stresses. Okay, if you don't have the Wolřejr stresses, you can compute here, or you can do you can compute here. You can do kind of a trick that you can scale this surface, then project your velocity into this surface and release the streamlines from that surface. Okay, kind of like when you do the post-processing, you capture those surface streamlines in paraview, in OpenFOAM, that you use a near U velocity. Okay, kind of that one. But here what you do is scale your surface, project, and do that. So that is very straightforward. I won't do it here, but I will show you how to do it, starting from the Wolřejr stresses and creating a matrix of points from which I want to release those strings. So the first thing that we need to do is just create that mask. Okay, so you see here that I'm creating, see those points there, I will release those streamlines from all those points. So how do we create those points? It's very, as always, we have many filters. It's a very complete tool. Okay, we have many sensors in paraview. Okay, and you see that I'm releasing the streamlines only from those points. So to create this one, again, you go filters, mask points. Okay, you can do that one, and you will have many options. Okay. So it's up to you to play around, but remember, you will need to select this one, generate vertices. If you don't select this one, you won't generate those points. Okay, and then you play with those options. Okay, these are okay. So I'm doing some random samples. So for instance, see that if I increase it to 1000, I will have my 1000 points, and then I can choose to release these streamlines from those points. Okay. So as you see, you can have incredibly control from in those streams. As you can also create the points manually projected here. Just play a little bit with the options. So the next step to release the streamlines is just another new filter that we see here is stream tracer with custom source. Again, you select your mask points. You go here and you access that filter here, and basically this filter, okay, will do something. I will select first. You need to select the source, okay, from where you want to release those streamlines. Okay, so I want to release those from the mask points, and my input is where I want to put those streamlines. So you can put those streamlines in your domain or just in one surface. So I know that strike block is my single surface, okay, the Ahmed body, and okay, and you will do your string slice. I won't press OK because I already have it. So here you see that, and then you will get access to many actions. So remember, you need to select the vector. So if you select U, you won't see anything because U is 0. So remember to select Wolřejr stresses and a few options related to that filter. But what is important that in this case we want to restrict this string lines to the surface. By default this is not selected. Just click there, select it, apply, okay, and depending on dimensions of your domain, how many string lines are you selecting, this can be a little bit time consuming. But see that paraview is doing the computation here, so let's see how long it will take. You can run in parallel, so probably, yeah, I think we need to do a tutorial dedicated to paraview just to show you how to run in parallel on some very advanced filters on programming in Python. So let's wait a little bit. Okay, here we have our string line. So as you see, okay, we have 1,000 points releasing from those 1,000 points. Our beautiful string lines following the flow as it were attached to the wall. That's all lines attached to the wall. Again, remember you can choose different value quantities to color those filters. I don't want to see that. Okay, start max point, and just plot that for U will be okay. U will be 0 by definition, and probably can plot that by P, and you see your students by P. So it's up to you. You play a little bit with your actions. Put it black. Okay, so probably it's better like this. So this is how you plot the string lines in your body. And let me see what else I can tell you. Yeah, I think I cover those basic filters. So again, remember, if you want to save a screenshot, you have the option there. Okay, it's not a problem. So I guess this is all for this tutorial. I think we cover a lot. Okay, so in general CFD as well in OpenFOAM, this is pretty much the same approach using different utilities, but this is how you run a simulation. I hope you find it useful, you enjoy it, and sincerely hope just to see you again. This wasn't quite easy. It was a little bit time consuming putting everything together, as we have many things to do. Thank you very much and enjoy.